Hello, and welcome to lesson 17 of this Introduction to Linear Algebra with Wolfram U. The topic of the lesson is diagonalization. So let's begin with a brief overview of the lesson. So in the last lesson, we talked about the similarity between matrices, and we said that if you have two matrices A and B, then they are similar if there exists an invertible matrix P such that A is P times B times P inverse. And in this case, we see that such matrices have got the same eigenvalues. So similar matrices have the same eigenvalues. And the point over here is that it looks like the relation over here doesn't depend upon A and B particularly, but in this lesson we'll try and talk about the case where the matrix A is similar to a diagonal matrix D. So the matrix B over here is going to be diagonal when that is possible. And in such a case, we'll say that the matrix A is diagonalizable. And the process of obtaining D starting from A is called diagonalization. Okay, so there is luckily a sufficient condition for this to happen, namely the case where you actually have n distinct eigenvalues for a square n by n matrix A. So you have a matrix A, and if you can check that it has got as many eigenvalues as the order of the matrix, then you have a diagonalizable matrix. And in such a case, there is a diagonal matrix D and a matrix P which is invertible such that A is equal to P times D times P inverse. And fortunately, it's very easy to find D, namely D is a diagonal matrix whose diagonal elements are the eigenvalues of A. And P also is quite easy to find out. The columns of P are the eigenvectors of A that correspond to the respective eigenvalues. So that's a nice sufficient condition for diagonality, namely you've got n distinct eigenvalues. So as an example, here is a matrix A. It's a 2 by 2 matrix. It has two distinct eigenvalues, 5 and 3. So what you do is you construct a diagonal matrix with those as the diagonal entries. You've got 5 and 3 over here. You find the eigenvectors, take a transpose, and you get the matrix P. And then finally you can check that A is equal to P times D times P inverse. As a second example, here is a triangular matrix. In fact, it's an upper triangular matrix. And we know in this case that the eigenvalues are going to be 1, 7, and 2. So in fact, let's check that. And you get 7 to 1 in the decreasing order. So let's construct a diagonal matrix with those as diagonal entries. Let's compute the eigenvectors of A, construct the matrix P, the transpose, and let's check that you actually have the similarity relation over here. So A is similar to a diagonal matrix with entries 7, 2, and 1 on the diagonal. Okay, now the main theorem for this lesson is the diagonalization theorem, which says that a square matrix is diagonalizable if and only if it has n linearly independent eigenvectors. So it doesn't matter how many eigenvalues there are, you need n linearly independent eigenvectors. And in such a case, of course, you have a diagonal matrix D and an invertible matrix P such that A is equal to P into D into P inverse. And once again, the diagonal entries of D are the eigenvalues of A, but this time, if the repetitions, you've got to have the correct algebraic multiplicities. And the columns of P are the eigenvectors of A. Okay, so as an example, here is a 3 by 3 matrix. Look at the eigenvalues. There are only two of them really, 5 and 2. One of them is repeated. But fortunately, we find that there are 3 eigenvectors, and in fact, they are linearly independent, as you can see away from determinant. So we construct the diagonal matrix, making sure that you have the correct algebraic multiplicity over here. So you've got 5, 5, and 2. Construct the matrix P. And finally, let's check that A is equal to P into D into P inverse. Okay, just to make sure that not everything can be diagonalized, here is a non-diagonal matrix. So here's the matrix A. It has just one eigenvalue, although it's order 2. And then you see over here that, in fact, you only have one linearly independent eigenvector because the second one over here is just a 0 vector. So this matrix cannot be diagonalized. And we have a nice function called diagonal matrix Q in the system, which can actually tell that to you straight away. So it says false over here, which says that this matrix cannot be cast into a diagonal form by a similarity transformation. So as a nice application of these ideas, let's talk about the powers of a matrix. So let's say you have a matrix A, a square matrix. Then you can compute the kth power of A by multiplying A by itself k times. So for example, here's a 2 by 2 matrix. You can compute A cubed by doing A times A times A. And we have a nice function called matrix power, which will do that for you quite directly. So you see over here that you get back matrix power A comma 3, giving you A cube in this case. Now, the nice thing is that if you have a diagonal matrix, then its powers are very easy to compute. Namely, you simply find the kth powers of the diagonal entries. So here is a diagonal matrix. You want to work out, let's say, the 10th power. So simply do 5 raised to 10 and 3 raised to 10, and you get back the answer. Let's check the answer with matrix power, and you do get back just the same result. Now, why is it useful? Well, suppose you have a matrix which is diagonalizable. So, of course, in this case, we have a matrix D, a diagonal matrix D, such that A is equal to P into D into P inverse. Now, it turns out that with this condition over here, if you want to work out the power of A, the kth power of A, then all you do is do P times D raised to K times P inverse. So really you don't touch P and P inverse, you simply find the kth power of D. So that's of course a great simplification compared to find the kth power of A. And as an example, here is a 2 by 2 matrix. Work out the eigenvalues, work out the eigenvectors. You see it's diagonal, so we work out the matrices D and P. I'm calling it D1 and P over here. Now, what you could do is you could work out, let's say, the 10th power of A directly, or you could use a relation which I just stated early on, that A raised to 10 is P into D raised to 10 into P inverse. Let's do that over here. So you do P into the matrix power of D1 raised to 10 times the inverse of P, and you do get back just the same result. So that's a very nice application of the idea of diagonalization. Namely, you can find the powers of a matrix by finding the powers of the diagonal matrix over here. Okay, so that is the end of this lesson. And so in this lesson, we've talked about the conditions under which a square matrix can be cast into diagonal form. And a sufficient condition for that to happen is that you must have n distinct eigenvalues. Now, of course, that may not happen always, but the nicer condition is that you can diagonalize if and only if you have n linearly independent eigenvectors. So that's the much nicer condition for having a diagonalizable matrix. And finally, if you want to find the powers of such a matrix, you simply compute the powers of the associated diagonal matrix. That's a great simplification. So that's the end of this lesson, and in the next lesson we'll talk about inner products and orthogonality of vectors. But I'll stop over here for today. Thank you very much.